Okay, let's have a look. So I saw a question from Tyler, I think. Yeah, so let's do it. Ooh, we're in green today. Okay. So let's see. All right. So we are. I'll just write down the elements here. We have boron 2 plus, lithium 2 plus, nitrogen 2 plus, and neon 2 plus. Okay. Let's just go through these. Today is review day indeed. I figured, your exam is next week. Not really. It'd be probably wiser for me to not keep throwing new material at you guys. Um, I mean, it just seems like that stuff is going to be on your final exam. Let's not do it right now when you have to be focusing on other material. So, because I mean, we're like about like 2 days ahead of schedule, so let's not worry about it. So let's go ahead and do some questions. So, of course, the rest of you who are here, go ahead and throw some questions out if you have them. That's what we're going to be doing today. Okay. So let's start with the boron one. So for all of these, I'm just going to get, except for the lithium, I'm going to forget about the 2s. So boron has just one electron in 2p. The other one will make our boron plus, has no electrons, therefore in 2p. So remembering that boron, carbon, and nitrogen, the first three in the p block, they have pi is lower than sigma. So we're going to see our pi at the bottom, because that is the lowest one. Here we have pi 2p rather. Oh my goodness. This is sigma 2p, pi star, sigma star. Put all these little dots around for some reason. Okay. So we have one electron here. That electron goes into its lowest energy orbital. Hooray, we're done. Very exciting. So let's go ahead and look at the next part of the question is cut off. But I'll leave it, I believe it was like if adding an electron is going to make it more stable or less stable. So if we were to have one more electron, that one in blue would be put there in the pi 2p. With the other one at least. And so that would mean that we start with a bond order of 1/2. After we add the blue one in though, we go to 1. So that means it's going to be more stable. Of course, the more electrons you can dump into bonding orbitals, the better things are going to be. All right, lithium, dilithium plus, oops. Here is our first lithium. Here is our positive lithium. We have 1 electron, 0 electrons. So again, we're going to end up with just 1 electron there. Bond order for that is 1/2. If we put in another electron in blue, we would get 1. Hooray. So again, that extra electron is going to make this more stable. Let me write that more stable. Nitrogen now, okay. We have nitrogen, has 3 electrons in p orbitals. We have a positive nitrogen, so it only has 2. Remember, nitrogen will also have pi as its lowest. I'm just going to not write 2p everywhere, if that's okay with everybody. Just making this a little neater. So we have 1, 2, 3, 4. I see 5 electrons total, so we'll put a 5th one there. Bond order for this guy is 2.5. Putting in our extra blue electron, we get a bond order of 3, so again that's more stable. Last one is the neon thing. It doesn't matter if you have one neon that's full and the other one is 2+. Doesn't matter. We're still going to have the same number of electrons overall. I just like making them the same. Remember, this one is not one of those 3 elements, so it will start at sigma being the lowest. We have 10 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Bond order for this is going to be 1. If we put in a blue electron, the bond order becomes 1/2, which is less stable. Well, that was exciting. So, looking at those, to be quite frank, Tyler, I'm not sure what your question was on those. Like, did you just want to kind of see them being done, or what were you kind of looking for there? Oh, okay, yeah. So, most of our elements will look like this one with neon, except for 3 of those ones. So yeah, you want to start off with having your atomic orbitals for the part you're interested in. Again, I've gotten rid of the 2p because we already know that past beryllium. I got rid of the 2s because we know that's already going to be completely full. So we're just kind of looking at the valence molecular orbitals here. So again, yeah, you could have taken one of these electrons and had one neon be full and the other one 2+. Doesn't matter. We're still going to get 2+ overall here. If we look at the next question you had was CN. Okay, let's look at CN. We had CN+, CN, and CN-. Both of these have the pi orbital as the lowest one. Remember, B, C, and N, pi is lowest. The rest of them, sigma is going to be lowest. So, here, let's just write it down here. So pi is lowest, then sigma, pi star, sigma star. I'm just going to go ahead and copy this so I don't have to draw it 1,000 times since we're doing the same 2. So let's start with CN+, I guess. Carbon normally has 2 p electrons, so carbon plus would just have 1 p electron. Nitrogen has 3p electrons. So we have 4 electrons total here. Oops. So 1, 2, 3, 4. And we're going to end up with a bond order of 2. If we have neutral CN, no ion, we're going to have 5 electrons total. So those are going to go like so. Again, we always fill lowest to highest, unpaired before paired. We get a bond order of 2.5. And if we do Cn minus, we can see what this is going to look like. Again, it does not matter which one you give the minus or plus to. I'm just in the habit of doing the electronegativity, giving it to the most electronegative one, but it does not matter. You could make carbon the minus one. Who cares? And in fact, in the polyatomic ion, that is the negative one anyway, but that's okay. If we look here, we have 6 total electrons. 1, 2, 3, 4, 5, 6. We have a bond order of 3. That one is going to be the most stable of all of them. Let me just go ahead. If we wanted to do the configuration for this, we would say this is pi 2p2. I'm sorry, 4. We have 2 of them in there. Sigma 2p2. I mean, just for practice, if we wanted to write the electron configurations, that's how we would do it. What was the question asking? Let's go ahead and take a look. It is saying which one is the strongest CN bond and which one has any unpaired electrons. Okay. If we look at that, the strongest bond is going to be our highest bond order. So our options are 2, 2.5, and 3. So that one is going to be our strongest. Highest bond order is going to be our strongest bond. That's going to be a triple bond in between them. And so we're going to have a nice happy polyatomic ion here. The other one is asking about unpaired electrons. If we look at this one, I do not see any unpaired electrons in this molecular orbital diagram. This one does have an unpaired in that sigma orbital. And in the first one, I also do not see any unpaired electrons. So the only one to have unpaired electrons is going to be the neutral one, Cn. Very exciting. Hooray. Awesome. Okay. Let's wait for more questions. By the way, on the practice exam that is on Canvas, there is going to be one that you're not going to worry about. Because there would just be no way for me to give that to you in a reasonable amount of time. So let's go ahead and let's open that up. So it is on Canvas in the extra practice. Is this the one we want? Yeah. The very last problem is one of those complicated lattice energy ones. That one you're not going to have to worry about. just because. Okay, here we go. That sort of thing, remember, is way too complicated to ask on an exam. Let's just put this here. So I've got another stolen exam here. It is on, if we look on Canvas, let's go, let me just show Canvas then. Okay. Okay, here's our homepage on Canvas, yes. Scroll all the way down to extra practice. I have here your exam, full practice exam 4, and then your key for it as well. So you'll be able to see the answers there. So if you click that, it's just the Word document, which will, for whatever reason, take forever to load on Canvas. Again, this is a stolen exam, but it's effectively got the same ideas here. The last one on this, don't worry about. This is essentially just a crazy Hess's Law problem, but that's quite a bit of work, and I don't want you guys to have to spend a ton of time doing something kind of similar to what we've done before. So don't worry about this one on your practice exam. You're not going to get something like this on your real exam. So yeah, exciting. What you just want to know about lattice energy is kind of the same stuff on the homework, like how charge affects it, how distance affects it. Oh my gosh, phone going berserk. Okay. So, yeah, take a look. Let me know if there's any you want to go over. It looks like today is Tyler's free review session day. The polarity stuff I would also not worry about because we're going to deal with that in the next one, because I had taught it in a different chapter. So yeah, I've got stuff on hybridization, bond angles, geometries, sigma and pi bonds, delocalized electrons. Remember, that's going to be your resonance sort of thing. So you're looking at these, which one of these will have resonance. Something about counting sigma bonds. Which one of these is not a resonance structure, you know, stuff like that. So yeah, we have plenty of fun to work on with this. Okay. For counting sigma bonds, remember that a single bond between two atoms is always a sigma bond. A double bond is 1 sigma and 1 pi. And a triple bond is 1 sigma and 2 pi bonds. So we're really just looking at how many single bonds there are. And looks like we do have one double bond. We know that one of those in the double bond is going to be sigma. So we would just say, okay, here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 sigma bonds. If I had this on paper, I would write them out, but not the case here. So in this molecule, we would see that there are 12 sigma bonds, and we would have 1 pi bond. I guess the question is just asking for sigma, though. So it's just a matter of counting how many single bonds you have, and then really just the number of bonds in total will be your sigma bonds. And then pi and all that would be for double and triple. If we look at this one, here, why don't we do this one? So let's, I'll switch back to our regular screen. I'll write it out. We had CH3, CH2, CCH. Oops. if we look at these carbons don't have enough bonds, so we would need to give them the extra bond. Yeah. So, well, let's look at this one. Let's look at, so we have a triple bond here. That's 1 sigma and 2 pi's. That's a sigma, 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 that's a sigma. So yes, we will definitely include one of those in a multiple bond to be a sigma bond. So if we look at how many sigmas we've written out here, 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 9 sigma bonds and 2 pi bonds in this, exactly. And so that would be answer C for this particular problem. Let's do another one. I guess I need to put the carbons in for you guys. Okay, crazy molecule here. Indeed. So all the other carbons are, yeah, so this would be, if we were looking at hybridization, these two would be sp, the other carbons would be sp3, if we're looking at those. Okay, crazy molecule here. Let's look at, we can do all sorts of things. Let's see how many sigma bonds total we have and how many pi bonds total we have with this one. This is quite a daunting molecule for this type of question, but we can do it anyway. I got 18, Kevin. Let me see if I got an answer. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. I got 18. I'm sorry, that was Tyler, not Kevin. I got 18. Double check your counting on that one. And then pi, 1, 2, 3, 4. Yeah, you're absolutely right on pi. So you should get 18 total sigmas, though. Yeah, awesome. Okay, cool. Yeah, I find it useful to just write the numbers next to it, so that way it's easy to see if I've counted it already. Now, interestingly enough, all of the carbons here are sp2 except for one. I'm just going to number all the carbons. Ah, that'll do it. Mm-hmm. So exactly. So carbon 8 is sp3. All the others are going to be sp2. Yep. So lucky for us, double bonded carbon or double bond anything will be sp2. If it's got a triple bond or 2 double bonds, then it's going to be sp. Other than that, sp3. Awesome. How about What's the bond angle here? A little less than that, Kevin. That would be for something trigonal pyramidal. Yep, I would agree with Tyler. That one should be about 104.5. Because that oxygen is AX2E2, that's bent. And bent ones have that 104 degrees. How about the angle? The angle between 10, 7, and 11. Just a way of locating where that angle is. Wow, green and purple is kind of a horrible combination. Yikes. Yeah, that'll be 120, right? Because that's SP2, of course. So it's trigonal planar. Barney. Oh, that's true. Yeah, he is green and purple, huh? But it's not like this weird kind of like lime green. He's more of a like. Actually, I don't know. It's been a long time since I've seen Barney, so can't quite comment on that. All right, looks like you're pretty good on that. Let's see, what else can we do? How do we feel about like? Were we okay with like the bond enthalpy? You know, breaking and forming bonds. It looked like at least Tyler, you were okay with those earlier, but let's see what else. Well, okay, you're good on that. Okay. You're apparently the only one to ask a question today. Kevin, do you have any? Or anyone else who's lurking around here? The homework keys are there as well. I did post them last night. So I guess Kevin, double check me as always. We'll see if I've got any calculation problems or extra zeros or whatever, but those are up there as well. The hybridization one is up there. Apparently something's happening over there. Well, we'll see, I guess, then, Kevin. I missed her. Yeah, so if you can do everything on the homework, you should be okay for the exam. And kind of the major topics we did were Lewis structures in general. We did electron geometries, molecular geometries. Remember, we had that lovely chart that's up on Discord for us there, so we could see what the shapes of all these things are going to be. Let's see, what else did we have? We talked about bond angles as well that result from those geometries. So you probably would want to review those. Let's look at what else we did in chapter 8. We of course had the bond energies, yes, for sure. We did formal charge as well. That was another one. Some lattice energy stuff. No gas laws. Just 8 and 9. So it's mostly all Lewis structures and then the molecular orbitals. That's pretty much it, but there's, of course, a lot of stuff we can do with those. I mean, you saw this one molecule that we threw up. We could do all sorts of different, things, hybridization, the bond angles, the formal charges, how many lone pairs there are going to be, how many sigma bonds in the whole molecule, how many pi bonds. Yes. Okay, so that was pretty much all of 8. Let's see what 9 was like. 9 was basically the shapes and the molecular orbitals. So just remember, diamagnetic means there's no unpaired electrons. Paramagnetic, you have unpaired electrons. More unpaired electrons you have, the better. More paramagnetic you are, I guess. Let's see. Yeah, that was pretty much it. And bond order. So if you can do those things, you guys should be set for exam 4. We'll have gas laws, intermolecular forces, liquids and solids on our final exam. That will be the majority of your final exam, and then you'll have sundry other bits of other stuff as well. But by and large, it's going to be focused on the last 3 chapters. Alrighty, so all these hateful molecular orbitals. It's a pretty messy homework key just because they take up so much space, and I hate doing that. Wouldn't that be funny? In fact, your final is only on thermochemistry. I've changed my mind. So it's just going to be very long, complex thermochemistry problems, and that'll be it. So, yeah, too late to drop. Okay, well, if there's nothing else, I mean, as always, just drop stuff in Discord if you have questions over the weekend. I'm happy to continue explaining stuff in words. Let's see. I did get a couple of partner requests for the lab thingy. So I'll take those into account, and then otherwise I'll let you know when I have your groups set up for you guys. And then next week you'll get your topic. So that'll be after the exam, you'll get your topic. You can maybe start meeting with your group, thinking about how you might want to tackle this problem. It would be a good idea to maybe spend some time next week looking at all the videos for the techniques and the equipment, because there is information in the videos about when you would want to use certain techniques. So that would be important for you come your lab experiment, because you want to know if you're going to be filtering a precipitate. They're in, if you look on Canvas, let's have a look. I think that's this one. In the videos and samples one, there's all these YouTube videos of various things. You've got just lab, what equipment is available to you. You'll have various like how to do these sorts of things videos, and as well there are some sample experiments. So for example, if you were to take this one, this is kind of what you're coming up with. Ooh, so this is a thermochemistry one. So this will be Tyler's project. So there's an introduction here talking about thermochemistry and all its lovely delights, bunch of equations, and then we're going to get into our kind of procedure part. So you'll also have your safety information. So if you're going to be working anything that's horribly corrosive, apparently this person has chosen to work with phosphoric acid, so they're going to put some like safety stuff, which is important. And then they're going to be doing this sort of thing, and then so you'll be just kind of putting up an experiment like this. So you don't have to worry about like the exact numbers like this, so long as it's not like 50 gallons of phosphoric acid and 50 gallons of ammonia. I mean, that would just be pretty wasteful. So try to keep it somewhat small, but not, you also don't want to do like 5 microliters of these. So usually milli is a good range for liquids to be doing, and then grams or hundreds of milligrams would be good ideas for solids. So yes, so those are some examples there. So this is essentially what you're doing. You're coming up with something like this. So this one is a lab designed to tackle the problem of figuring out the identity of an unknown metal by its heat capacity. And apparently there's also doing other things, but you're only going to have one kind of topic to work with. Okay. So again, you'll see that next time. So that thingy, all these videos are pretty short. They're like 5 minutes or so. So it'll probably take you like an hour to go through them all, I guess. Something like that. And that should give enough of a basis for some ideas of what you want to do. I would recommend, after you have some idea, to run it by me. Say, hey, what do you think about, I'm gonna, for this calorimetry thing, I'm gonna try, or I'm gonna identify this thing by its heat capacity, but I was wondering how the heck am I gonna measure the temperature of the metal or something. I can give you some ideas or whatever. But again, you guys are going to be the ones coming up with the major parts. I can maybe help you figure out how to measure a particular thing that you would need for calculation, or to maybe say, hey, here's another resource you can come up with that has all the reactions of copper or something. I don't know. Kevin, of course, already has all the answers. That's how I would recommend you do it as well. So typically, if you want a hot piece of metal and you want to know what its temperature is, you put it in boiling water, you measure the temperature of the water, your temperature of the metal should be the same. So, for sure. So I guess whoever gets Kevin will be very lucky. They will not need to speak to me about their lab project. So, alrighty. Well, guess that's it for today. So with that, you have 5 more days, I guess, to study and have election anxiety and all that fun stuff going on. So, exciting. Okay, well, with that, I guess we will finish for today. I'll post this up for you guys. But yeah, just let me know if you have more questions as you go through the weekend. Did I put homework up for you guys, by the way? I think I did. I put your gas loss stuff up. So that's up there somewhere as well. I guess it's kind of hidden. I'll make that more visible to you guys. Yeah. Alrighty. I'll see you guys Monday. No, not Monday. Tuesday. Wow, almost a whole week. Okay. See you guys then.